Good afternoon, everybody. Thanks for coming to the seminar today. We're very pleased to have our industry speaker, Dr. Guangyi Liu from Garena. And as many of you know, Garena has been our industrial partner, sponsoring several projects and also hosted several intern students and also hired a few uh, current graduates. So, today, let me introduce the speaker a little bit. Our speaker is Dr. Guangyi Liu. He is the Chief Technology Officer of Global Energy Interconnection Research Institute at North America, or ARENA. He received his bachelor's degree from Harbin Institute of Technology in 1984, and his PhD from China EPRI in 1990. Then, over the past a few decades, he worked at ABB California location in the ABB's EMS system, and also New York ISO. So he had a lot of real experience with the EMS system. Right now, he's leading a team at Garena doing EMS system and also graph computing. And his presentation topic is graph computing and its application in power system. And please join me in welcoming Dr. Liu's presentation. Okay, Guangyi, are you ready to start?
Yes.
Okay, please go ahead.
Thank you, Professor Li, for your introduction. Hello, everyone. My name is Guangyi Liu, CTO of the Gary North American. And the Gary North American is a R&D company located in San Jose, California. Right now, we have more than 40 researchers, and then we have a few openings for full-time and summer intern right now. Today, I'm very glad to have this opportunity to present our research work on the next generation EMS using the graph database and the graph computing technology. I will first introduce the next generation EMS roadmap, and then talk about the issues of the rational database that the conventional EMS is using. We propose graph modeling, computing, visualization to solve the issues which will be presented in the third section. And then I will use a couple case studies to show the advantage of the proposed graph computing. So basically, EMS, energy management system, is a critical software platform used in almost every modern power system control centers. It has been developed for decades. The first one can be traced back to 1970s. After 1965, the famous blackout in New York City. Here is the roadmap for the next generation EMS. It can be divided into 5 stages. The first one makes it bigger. It means it can solve big problems. For example, the budget in PGM EMS is around 16,000. For the meso is around 40,000. The second stage is to make the EMS system stronger. It means that it can work under all situations 7 days, 24 hours. The third stage is to make the EMS faster, means it can solve the problem very quick. The fourth stage is to make the EMS smarter, more intelligent. And the fifth stage, that is the final goal, is to develop the EMS route using the advanced database technology, parallel computing, natural language processing, deep learning, and situation awareness and autonomous dispatch to provide real-time, proactive, intelligent, and predictable operating system in control center. Right now, we are in the second stage. EMS network analysis function is running every 1 to 5 minutes. During this 1 to 5 minutes, if some events happen to drive the power system crazy, operators may be unaware of them until next EMS running cycle. In such situation, when the operator notices the problem, it may be too late to take actions to avoid the potential blackout. This makes the power system operating at risk. To make the system more awareness and to solve the above problem, we have to speed up the applications, improve the performance. Then the application software can give operator more time to take actions to avoid power system blackout. Our work is focused on the third stage, that is how to speed up the application using the new technologies. So in this slide, the left one is the current EMS system used in almost all the control centers. We can see the data, the scatter function collects the data from the field through the communication network on the RTU. And then the raw data is get into the real-time database. We will use the topology processing to convert the node break model into the bus branch model. That is the calculation model. And then we can using the state estimation, security analysis, and economic dispatch to do the analysis to see if the system is running in the good status or not. From here, you can see for different applications, they use different database. For example, in the real time, they use a real-time database. And in the maintenance, they use a maintenance database. For the planning, they have the planning database. And here the same, this is an AEC SIM. This is called a common information model, is used to exchange the data among these functions. So this one, basically it have the features like they are using the rational database, and they use separate data model for different applications. And the visualization is not interactive. It lacks the intelligence. The red one is the future EMS using the advanced AI technologies. It requires more complicated data model, intensive calculation, dynamic man-machine interface. Of course, it demands faster computing. It can be the high-performance computing is enable technologies to make the EMS smarter and more intelligent. Why we need to develop the super fast EMS? As the high voltage AC and DC transmission lines put into operation, power electronics will dominate the largest and the most complex human-made system. That is our power system. And as the more renewable energies integrated into the power system, the load curve has a big change. For example, the famous California dark curve, the peak load is not happen during the day. It happens at the evening. And the rating rate is very high during 5 to 7 p.m. As the DOE report pointed, with the power system getting larger and more complex, the possibility of more events we must be aware is getting higher. We must make a system more awareness and more sensitive. Today's managed system view has to be replaced by the scalar sample rate. That is 4 to 6 seconds view. So basically, there are three kinds of EMS applications. The first one is a monitoring visualization function. Their time scale is tens of seconds to minutes. The second kind application is intelligent alarming, queuing, and decision support. Its time scale is seconds. And the third one is automatic control. Time scale is sub-seconds. The sub-second analytical processing time can enable some critical functions, such as network constrained AGC, online SPS alarming decision, and heavy loaded power-flow accurate solution. US DOE requires to develop state estimation at 0.5 seconds speed for medium-sized power system. DOE already funded $220 million to develop the high-performance calculation analytical tools in the past few years. This is a comparison between the commercial EMS with our EMS prototype. From this slide, you can see the SCADA sample rate usually is 4 to 6 seconds. Here we can use 5 seconds. In the commercial EMS, right now the EMS network application execution cycle is from 1 minute to 5 minutes. Usually, the data estimation execution time is around 5 seconds, per flow around 4 seconds, and the condition around 20 seconds. When we use our graph computing-based EMS prototype, the EMS execution cycle can be reduced to 5 seconds. And the state estimation execution time is around 400 milliseconds, and the power flow is around 70 seconds, and the condition analysis is around 1300 milliseconds. So compare with the commercial EMS, our EMS prototype, the performance improve almost 15 to 20 times. So this is the main display for our super fast EMS. Sorry for this one is in the Chinese, but here we have basically have 4 functions. The first one is network topology processing. The second one is state estimation. Then the third one is online power flow, and the fourth one is security analysis. From here, you can see for the state estimation, its running time is 139 milliseconds, and for the power flow is around 56 milliseconds, and the security analysis is 1322 milliseconds. In order to speed up the EMS application performance, first we need to see what's the problem for the commercial EMS system. The traditional EMS system usually use rational database to model power systems. So it uses a lot of different tables. Rational database does not support unstructured data. The length of each table is fixed. If you have a device with different numbers of attributes, you need a new table. Rational database uses shared key value to represent the data relationship, which is not straightforward, and need bridge table to create connectivities. Usually, it's very hard to maintain rational database. For example, if you need to remove a bus or node or elements, all elements connecting to this bus need to be updated in their associate tables. This is very time consuming. And let's see how it works when we're using the rational database to create the applications. For example, if you want to have a path flow application, first you need to retrieve the data from the rational database into the C programming. Then you need to do the data pre-processing to use the data from different table to create the maintenance matrix or JACB matrix. Then we can using the algorithm to do the call calculation. After we get the solution, we need to map the solved variables to bus voltage and the branch flows. In this way, you can do the visualization on the display. So from here, you can see the data input pre-processing and output traversal is necessary. You can't avoid it. This slide gives you a real case. This is a 2650 bus system from a provincial power system in China. So here, this is the power flow and the state estimation calculation time for this system. So for the power flow, it takes 3.8 seconds, and for the state estimation, it takes 4.5 seconds. And when we further to investigate how the time is spent, we can see for the power flow, the data input processing and output traversal cost 94.5% of the total time. And for the state estimation, their data input processing and output traversal cost 65 total time. So from here, we can see we need to find a new database or new platform. For this new platform, they can integrate data management, calculation, and the visualization together. In order to further improve the performance, we will decompose the call calculation for the path flow. From here, we can see the call calculation part can be divided in two kinds of calculation. The first one is matrix formation and the PQ calculation. That part costs 45% of the total time. For this kind of calculation, because they don't need the matrix calculation. So for all these calculations, they can be using the nodal parallel computing technology to solve. And for another part is a matrix related calculation, like the matrix factorization and the forward-backward substitution. So that part takes 51% of the total time. For this part, we need to think to using the hierarchical parallelized computing to solve. And this is the data estimation. We see the similar things. So basically, the calculation can be divided into two groups. The first one is related to the matrix calculation, formulation, on the right-hand side vector calculation. And another part is for the matrix factorization on the forward-backward. And so for these two different calculations, we need to using the different technology, different parallel computing technology to solve. So in this way, we can speed up all these network applications. So after investigating the issues of the rational database, we find that there is a new database they call the graph database. Using the graph database to model the power system is different from what we do by using the rational database. So the graph database, they use the graph structure, that is the node on edge, a node to model the data. And they store the data by attributes of the nodes on the edge. And they can support parallel computing. That the parallel computing, and it's very easy to maintain the large system. From the left picture, you can see when we using the rational database, all the data stored in the database is a collection of the interlinked table. But when we store the data in the graph database, the data model basically is a multi-rational graph. So this graph is very similar to the structure of the matrix, so we can use them directly. And from this one, this is the left one is a rational database-based computing. As we talked before, they need the data preprocessing on the output traversal to handle the data. But when we using a graph-based computing, we can integrate the system modeling, the call calculation, and the results visualization in the graph database. So in this way, the data input, preprocessing, and the result output traversal are not needed anymore. So in this way, and we can change the calculation approach from the serial computing to parallel queries. And we already implemented a suite of computation queries as a library for power system application. That means when we're using the graph database, we don't like the commercial EMS using the C++ or Fortran functions to do the call calculation. Instead, we're using the graph database queries to do the calculation. So in this way, it can speed up the application very fast. And this slide gives the general parallel algorithm structures. So basically, there are two graph computation models. The first one is called the all nodes synchronization. It means when we do the calculation, all the nodes are activated in one super step. This mode can be used in network data processing, such as the formation of the admittance, Jacobi, and the gain matrix, and the calculation of the output results on the violation checking. For the power flow solution, it can be used in Gaussian-Seidel iteration and the conjugate gradient iteration based power flows. The second one is called the hierarchical group synchronization. It means that in each super step, only one group of nodes are activated. So this mode can be used in the matrix aerial factorization on the forward-backward calculation. So this is the vertex-oriented graph parallel computing method. All the calculations only depends the nodes on its neighbor. And the data exchange among the nodes is using the message passing. So in this kind of calculation, the parallel computing mode can be using the node So this is the extreme form of the parallel computing. It means all the nodes, the calculation on all the nodes can do at the same time. And this is a typical graph parallel algorithms. It's very suitable to solve the following problems. The first one is a collaborative filtering. And the second one, they can use to solve structured prediction. And the third one is a semi-supervised machine learning. And the fourth one is a community detection, like the triangle counting. The fifth one is a graph and analytics. And the last one is a classification for such as like the neural networks. And this is the Perigo. Perigo is a graph computing framework proposed by Google in order to solve the large-scale PageRank problems. So they published this paper in 2010. So in this computing mode, there are three stages. The first one is called computing. So basically, this is called the local calculation. All the calculation can be done at the same time for all the nodes. The second step is called the communicate. The nodes send their message to their neighbor nodes. Then the third step is called barrier synchronization. So basically, the vertex program interact by sending message. That means they communicate through the message passing. This is the code which is widely used by Google search engine. There are three steps. The first step is for all the nodes receive all the messages from their neighbor. The second step is update the rank for each node. And the third one is send the new message to neighbors. So we use this method in our calculation for the power flow estimation and the contingency analysis to do the nodal parallel processing. And this is another widely used application based on the Perigo. It's called the connected components. So basically, for this example, we want to group the nodes by their connectivities. So basically, from here we can see there are two groups. The first one is node 5, 6, 7. The second group is 4 to 4, node 1 to 4. So how it works when we're using the connected components? So first, they will send the forward message, and then they will send the message and assign smaller value. And finally, we will get this after all the nodes is assigned the smallest value, it's done. So in the large step, you can see for the nodes 1 to 4, they are assigned the node value is to 1. It means they are in the same group. And for the nodes 5 to 7, all the nodes are assigned the value to 5. It means these three are in the same group. So basically, we use this method in our network topology processing algorithm because this calculation they can be done in a nodal parallel processing mode. On this slides show us the relationship between the matrix and the graph. So basically, for the symmetrical matrix, they corresponding to the direct graph. And the symmetric, they corresponding to undirected graph. For the triangular matrix, they corresponding to a directed acyclic graph. So from here we can see for each kind of matrix, they always have a graph corresponding to it. So in this way, we can implement it, the matrix LU factorization program using the graph technology to implement it. So basically, there are three types of graph computation. The first one is called graph structure computation, including the non-zero counts, non-zero structure formulation of the matrix, and how to form the elimination tree. And the second type of the graph computation is called graph modification, such as graph addition and graph deletion, including creation and modification of matrix, and the numerical factorization. And the third type is called graph property calculation, such as the triangle solver. Here is the algorithms for the LU factorization and the solver implemented using the graph technology. The first step is a minimum degree order. So this is a graph structure problem. And the second step is E-tree symbolic factorization. So this can be modeled as a graph modification problem. And the third step and the fourth step, the numerical factorization on the triangular solver can be implemented using the graph property calculation structures. So this is the node breaker model. When we're using this model, this is based on the base value, substation, bus, AC line unit, transformer load, compensator. So they are modeled by the vertex. And the data format we're using the common information model. This is the IEC standard. And we use the connected component we just talked about is using this method to do the network topology processing. So using this one to convert the node breaker graph to the calculation graph called the bus branch graph. So this one is the substation one line diagram in the commercial EMS right now. So this one line substation one diagram is drawn by the human manually. So it's very time consuming. When we're using the graph database, so this substation one line diagram can be created automatically using the graph analysis program. So basically it's very dynamic. We can, on this one, we can show the telemetry data, we can show the breaker status change, and then we can show the power flow solutions, data estimation solution on the SCADA telemetry data. And this one give us the graph-based Newton Raphson and fast decoupled power flow algorithm. So from here we can see the color. The red color. For the red color, basically this is involve the matrix formulation and the calculation del P and del Q and do the converge checking. So on the include the power flow computation and the output results. For all these parts, they can be using the nodal parallel processing. And for the current part, basically this involves the matrix factorization calculation and the forward backward substitution. So in this part, we're using the hierarchical parallel computing technology to implement it. And this is a graph-based state animation. So we can do the same thing for the basically for the red part. We can using the PageRank nodal parallel computing technology to implement it. And for the matrix factorization part, we will use the hierarchical parallel computing to implement it. So this is the comparison between the rational database and the graph database we develop the EMS network applications. So as we talked before, when we're using the rational database, we have to have the two steps. First, it's called the pre-processing. We need to search bars table, branch table to find the connectivities. And after we get the results, we need to using the output traversal to map the solved variables to bus voltage and the branch flow. But when we using a graph database, because all the calculation is implemented in the database query, so we don't need the pre-processing part and the output traversal part anymore. From here, we can two-match the comparison, the performance comparison between the two technologies. When we're using the graph database computing, we can see for the path flow, the calculation time is reduced to around 90 milliseconds, and the path flow is reduced to 200 milliseconds. So based on these numbers, we can see the path flow estimation, the performance has a very big improve. When we're using the graph computing library, we develop the EMS platform, and we achieved the super fast performance. The scatter sample rate is 5 seconds. For the data estimation, path flow, and the condition analysis can run and update every 5 seconds. So this slide shows the main page of our super fast EMS for the Sichuan province power system. From here, we can see the estimation takes around 200 milliseconds. Path flow takes about 56 seconds, and for the condition analysis, it takes 900 milliseconds. And here we have more than 1,800 contingencies fast screened, and for 100 contingencies analyzed using the detailed path flow calculation. So total from the topology processing plus the path state estimation plus the online path flow and the contingency analysis, all the time, the sum of the time is less than 2 seconds. On this map, each red node represented a bus. So the bus is connected by the transmission lines. When we click the nodes, they can show up the substation one-line diagram. And the location of each substation is given by the coordinates storing in the graph database. And at the same time, the map also shows the voltage heat map to indicate the voltage level on each bus. Now we come to the conclusion. So we can see the in order to solve the more and more complicated power system problems, the EMS cycle should be speed up as power system is significantly evolving to be large and more complex, with more power electronics, higher uncertainty, and faster events. And the fast and predictive analytics are critical to respond to cascading events, avoid the serial blackout and enable the advanced state information control. Under the high performance computing, such as the graph database and the graph computing and the graph parallel processing, give us the new technology to help us to meet the gap on the pathway to EMS robots. And we can see the graph database and the graph parallel computing is very promising to achieve this kind of super fast EMS. So this is all my presentation, and thank you very much for your attention. I'm very glad to answer the questions. Thank you.
Dr. Liu, thank you for the interesting presentation. So now we are in the Q&A session. Okay, Dr. Liu, can you hear me? Can you hear
Yes.
us? Okay.
Yeah, we can. Yeah, we can.
Any questions?
Yeah, I have some questions.
Oh, okay. That's the online users. Yeah, please go ahead.
Can I? Okay.
Yeah.
So excellent presentation. Thanks. It was very interesting. So I have a few questions. The first one is, this LU factorization, forward-backward substitutions, these are inherently sequential operations. So is there a theoretical upper limit to how much you can speed up these? Because this is an old problem. A lot of people worked on it to parallelize these, but there is an upper limit because of the inherent sequential characteristics of these computations. So that's my first question. I know that you mentioned this hierarchical parallel approach, so maybe you can elaborate on the properties of that and the limits. The other one is, I noticed that your state estimator is a fast decoupled state estimator, and then the pseudocode did not include bad data processing. So those timings are good, but of course that's not the true timing, because you need to actually go through the bad data processing each time you run it. So depending on the number of bad data, this can really hurt the CPU time because there is no figures given for the covariance estimation. How much time it takes to calculate the covariance matrix to do the bad data processing. So can you just give us some information about how you do the bad data processing?
Yeah.
So that's my second question. And then the third one, and that's going to be my last. You mentioned this node breaker to bus branch conversion using the topology processor. But as you know, some contingencies are not transportable to the bus branch model. And there are certain breaker contingencies which you cannot exactly transport and model in bus branch model. And that's primarily why the industry is moving to node breaker models now. So if you have any experience with that, I would love to hear that. Yeah, thanks again, and a very nice presentation.
Thank you very much. I'm very glad to answer your question. So for the first one, basically we did some comparison between the matrix factorization and the forward backward substitution when we're using the graph technology, and compare with because we have another partner EMI system using the traditional C++, the matrix factorization program. When we compare with them, our performance is for this 2650 bus system for the matrix factorization and the backward forward substitution for this small case the improve for this part improve is almost 2 times. And when we try to compare with a large system like the 10,000 bar system, or we created some fake system using 10,000 bar system together. For that part, it improved, say, 3 times. And for the second question is for the state estimation. You mentioned that for the data by data processing. So for that part, right now we are working on that, and we got some conclusions. So basically, for that part, we will participate for the whole network in different parts. So in that case, based on the biodata, we can divide the network graph into a few small graphs. So in that case, for all the small graphs, they can be done parallel process. For that part, because right now when we see the Sichuan, this is the Sichuan province in China. So basically, we see their telemetry data is pretty good. And so each time we don't have that many bad data, very few. So most time is only about 10. So the bad data processing doesn't take too long time. It only increase another 20 to 30 milliseconds. And for another part, you just mentioned for the kinetic analysis, how they using the node break model. So this is a very good question. So basically, because in a graph database, so in the database we maintain 2 graphs. One graph is called the node break graph, and the second one is the bus branch graph. So basically, from the bus branch graph, it's very easy to get the node break graph. So in this, right now we didn't do the condition analysis using the node graph, node break model. But I think it's because they all model into using the graph, so it's more easy for us to get from the bus branch model to get the node break model. So I think it should be the strength for the graph modeling. Thank you.
Okay, thanks.
Any other questions from the online audience? If not, then at UTK side, any questions from the audience? Yes, Anton.
Yes, thanks, Dr. Liu, for the nice presentation. So on slide 29, you showed the graph about the acceleration, like in the input processing, like core calculation output, and all of them show very high rate of like speed up. So my question is there any kind of formulation improvements, for example, in the power flow problem? If we formulate it in the, for example, the polar or rectangular like power mismatch formulation, then the LU factorization speed up, like if implemented properly, shouldn't be that like 10 times faster. And for a 2000 bus system, usually in Mat power, it takes like 0.1 second to do the whole processing. So so the comparison time for the conventional method seems a little bit high. Could you like elaborate on that?
Oh, so this is because this is
slide 29.
Yeah, I know. So this is because this is not the pure power flow call calculation time comparison. So basically, this is EMS application. So usually for the EMS application, when we implement it in the EMS applications, for example, for the power flow or the state estimation, they need to first they need to read the data from the database. After they do the calculation, we need to send the data back to the database for visualization and for the further analysis. So when you compare the pure calculation for the power flow, we don't improve that much times. So this is only two times or 3 times. But because this is software, is not the program, power flow program. So we need to compare the whole time from you gather the data and do the call calculation and you send back the results to the database. So when you compare this kind of time, because when we're using a graph database and a graph computing, so basically the most time we saved is for the input pre-processing and the output traversal. So this is why when you compare the EMS applications, we can see the big improvement. But when you compare with the pure call calculation, we don't have that much improvement for the performance. I'm not sure if answer your question.
I think it's yes.
Yeah, because of
you go ahead. Okay. Any other questions? Any other questions from the online audience? Okay. If no other questions, then we conclude today's seminar. Let's thank the presenter, Dr. Guangyi Liu from Garena one more time.
Thank you very much.
Okay, Dr. Liu, thank you.
Thank you.
Have a good weekend.
You too.